Good afternoon, everybody. I'm Dr. Joe Dorenzo, the Deputy Regional Coordinator for the Northeast Region for the Federal Lab Consortium, and I have a great webinar for you today. I will be introducing Dr. Brian Baum from MIT Lincoln Lab. We're going to talk initially about the Strive Center that he'll be giving you the background on. We're showing you a short video. I'll tell you a little bit about his background, and then we'll go immediately into his presentation. We look forward to your questions. You can either place them in the chat or ask them on audio. So let's talk about the Strive Center. MIT Lincoln Labs Sensory Motor Technology Realization in Immersive Virtual Environments, or STRIVE, Center is an approximate 4,000 square foot research facility located in Billerica, Massachusetts, about 6 miles away from the main laboratory complex. At the center of STRIVE is a 24-foot virtual reality dome, a computer-assisted rehabilitation environment, or CAREN. In this dome, a user experiences immersion, or the feeling of being present in a simulated world. The user can interact with the environment, which is displayed on a screen that wraps 360 degrees around them, while ambulating or balancing on a 6-degree freedom motion platform that mimics the environment's terrain. A motion capture system measures and analyzes the user's moments in real time. Additional sensing systems are integrated for multimodal data collection and analysis. This facility allows laboratory staff to collaborate with clinical, academic, and government communities on new research. In the area of clinical research, laboratory staff with clinicians to study patients' cognitive and physical performances and to test rehabilitation techniques. For training purposes, the CAREN system is a valuable tool to learn how service members or first responders can best develop and optimize skills in a realistic yet simulated scenario. The data collected from these interactions can help commanders plan more effective and safe missions in the field. The Strive Center also offers researchers a facility in which they can assess prototype technologies, such as wearable sensors, heads-up displays, or robotic exoskeletons in a realistic environment before it transitions to the real world. We're now going to show a short video.
The Strive Center at MIT Lincoln Laboratory is a 4,000 square foot facility that promotes collaboration among government, academic, and medical communities in order to tackle challenges in clinical rehabilitation, wearable technology development, and advanced operational training. The hub of the center is the CAREN system, an immersive virtual environment that enables comprehensive assessments of biomechanical, physiological, and cognitive performance. It is equipped with a motion capture system and a split belt instrumented treadmill mounted on a 6-degree of freedom moving platform. The CAREN system integrates electromyography, eye tracking, speech recording, powered exoskeletons, and other advanced sensors for thorough analyses of human performance. The Strive Center also has space for clinical assessments and ergonomic analyses, providing a comprehensive research environment for sensory motor technology development.
This now gives me great pleasure to introduce Dr. Brian S. Baum, who's the Research Director of the Strive Center. As a technical staff member of the Human Health and Performance Systems Group and Biotechnology and Human Systems Division, Dr. Baum focuses on objective technology-based human-centered solutions to measure, model, and modify biomechanical, physiological, and cognitive functions for enhancement, sustainment, or recovery. Dr. Baum's expertise relates to the healthy and pathological biomechanical performance of locomotion at the joint, limb, and whole body level, with application towards improving clinical care and optimizing the performance in prosthetics, exoskeleton, rehabilitation, orthopedics, military, and sports settings. Prior to joining MIT Lincoln Lab, he served as the associate professor in the School of Physical Therapy and Health and Exercise Sciences program at Regis University in Denver, Colorado. Preceding that, he worked as a portfolio manager for the Department of Defense Clinical and Rehabilitative Medicine Research Program as a biomechanist at Walter Reed Army Medical Center in Washington, D.C., and a manager of the Motion and Sports Performance Center within the Department of Orthopedics at Baylor University Medical Center in Dallas, Texas. Dr. Baum received his BS and his MS in kinesiology from Louisiana State University and a PhD in kinesiology with a focus on biomechanics from the University of Maryland, College Park. It is my great honor to introduce Dr. Baum.
Well, thank you very much, Joe. I want to thank you, Jamela, and the Federal Lab Consortium for inviting me here today, and thank all of you for joining me. So I am going to give an overview of the Strive Center, which you've already heard a little bit about and seen a short video. Again, my name is Brian Baum. I'm the Research Director of the Strive Center in the Human Health and Performance Systems Group at MIT Lincoln Laboratory. Before I jump into the Strive Center, I wanted to give a brief overview of MIT Lincoln Laboratory for those of you who may not be familiar. So MIT Lincoln Laboratory is part of Massachusetts Institute of Technology. As you can see from the map here, we're about 15 miles away from MIT's main campus. We're located in Lexington, Massachusetts. And our mission is technology in support of national security. So we work with the government, we work with the Department of Defense to provide system architecture engineering, long-term technology development, and system prototyping and demonstration. MIT Lincoln Laboratory houses approximately 4,500 employees, and in FY23, we had funding of right around $1.3 billion. We are a DoD federally funded research and development center, which allows us to work very closely with the Department of Defense and the US government. You can see our core mission areas on the left there, ranging from air, missile, and maritime defense, to communication systems, to cybersecurity and information sciences, space systems and technology, and so on. Our main responsibilities at MIT Lincoln Laboratory are to provide open and unbiased support to the government and develop non-competitive relationships with industry. So in order to do this, we develop and maintain strong technical expertise. We promote technology awareness, enable rapid assessment and prototyping capabilities, and really promote technology transfer from the government to industry. One of our divisions, which is the division that I'm a part of, is the Biotechnology and Human Systems Division. Our mission here is to accelerate systems and technology development in order to improve the health, performance, and security of our armed forces, veterans, and civilians. There's 5 groups within the Biotechnology and Human Systems Division, which includes health and performance, counter weapons of mass destruction, human systems resilience, biological and chemical technologies, and bioanalytics systems and technologies. And across these groups, we provide systems analysis, technical innovation, architectures, prototyping, and developmental testing and evaluation capabilities. In addition to working very closely with the government, we also have a large number of strategic biomedical and biotechnology partnering with academic, clinical, and industry partners, where MIT Lincoln Laboratory provides those system analysis integration and technology development and prototyping capabilities. We also help with the coordination and collaboration with these partners. You can see in each of those domains, the number in parentheses, those are the number of active collaborations we currently have ongoing in our division. So 46 academic partners that we have ongoing projects with, 28 clinical partners, 43 industry partners, and 75 US government research partners. Within our division, I'm also part of the Human Health and Performance Systems Group, where our mission is to develop advanced technologies in order to measure, model, and modify cognitive and physiological function that enhances human capabilities for national security. Our 4 core mission areas within our group are health and resilience, medical operations, operational readiness, and training and education. And we have core capabilities that you can see there, developing field forward health and medical technologies, human augmentation solutions, and advanced learning capabilities. We do this through cross-cutting expertise, such as human signal processing and AI analytics, systems architecting, human physiology, neuroscience, and cognitive sciences, and human-machine teaming. So there's a large number of factors that can challenge human health and performance that you can see here on the outside of this bubble. Things like environmental exposures, injury, fatigue, cognitive load, disrupted sleep. And our group uses the OODA loop, the observe, orient, decide, and act, in order to manage these challenges. So the first thing that we do there is to observe that challenge, and then orient ourselves to how that challenge is influencing the person. In other words, what's the human response to that challenge? Next, we need to decide on, and we develop response options and apply technology solutions in different domains in order to improve human effectiveness. And finally, we can act with appropriate interventions in order to assure the mission performance at the individual, team, and enterprise scales. We have a number of core infrastructure and facilities, including in the upper left, you see the chemistry, biology, and advanced analytical laboratories. We have rapid prototyping laboratories in the upper right there. We are able to generate threat and health effects simulations, and we have immersive environments for cognitive and physiological monitoring. And this is where I'm going to give a lot more detail today, is with one of our immersive environment labs, the Strive Center. So the Strive Center, as Joe mentioned, it stands for Sensory Motor Technology Realization in Immersive Virtual Environments. It's located in Billerica, Massachusetts, which is about 15 minutes from our MIT Lincoln Laboratory campus. It's a 4,000 square foot facility that was founded on sponsorship from the Department of Defense and the Director's Office at MIT Lincoln Laboratory. And the Strive Center is really intended to serve as an MIT Lincoln Laboratory-wide and a US government-wide resource. You can see in the map of our center there, the upper right corner is the Cairn system, and that is the core facility within the Strive Center. Cairn stands for Computer Assisted Rehabilitation Environment. And here you see a time-lapse video of the Cairn system being built. We had to dig a pit 6 feet down into the ground and pour some concrete in there. We have a 6 degree of freedom motion platform that you see being lowered down into the pit. On top of that is an instrumented split belt treadmill and a platform around that. You'll see these arms going up and bracing, which is where we mount our dome projectors and our motion capture system, which form some of the core components and features of the Cairn system. And then the inner dome, which is isolated from vibrations from the bracing around there, the inner dome serves as the area that the projectors can project that 360 degree image onto them. And in the end, we end up with a low latency real-time system that can generate unique immersive environments for quantifying human performance in operational settings. We like to think of the Cairn system as a flight simulator for dismounted activities. And so we can take a large number of sensing modalities. Here you see a powered exoskeleton. You see the person walking on the treadmill there with motion capture, with the markers that are placed on the body to do marker-based motion capture. We also have markerless motion capture capabilities, electromyography for muscle testing, vocal monitoring and eye tracking. We can measure ground reaction forces, etc., all while simulating environments driven by the Unity 3D gaming engine. In addition to the graphic environments there, we also have a 360-degree video stream options. We have targeted spatial audio. We can project in night vision, and we have an enhanced self-paced gate. So we are able to develop highly instrumented, flexible, immersive environments that have not only high real-world fidelity, but also comprehensive ground truth. One of our goals with the Strive Center and the Cairn system is to create a bridge from the laboratory to the real world, where the laboratory or a clinical environment typically has very highly controlled inputs. There's a lot of instrumentation that are used in laboratories. You can create multiple different possible scenarios, but a lot of times one of the downfalls of the laboratory is that it has low to modest real world fidelity. And if we want to translate technologies from the laboratory to the real world, we need to boost that real world fidelity. Now, the real world has its own challenges. There's uncontrolled inputs, which creates a lot of problems from the research side of things. You have to rely on wearable instrumentation, which may not be gold standard. You have to rely on very few scenarios. If you want a city scenario, well, you have to bring people to a city. If you want a forest scenario, you have to bring people to the forest. And that can be a real challenge from a time and money standpoint. But of course, the real world has real world fidelity. So immersive environments can act as this bridge between the two. And it draws on the best aspects of both the laboratory and the real world. So we have the ability to control our inputs and have that ground truth. We have a highly instrumented environment where we can validate wearable technologies. We can generate many possible scenarios by simulating the real world, but we also have high real world fidelity. And that allows us to rapidly iterate on technologies, reduce our risks, and increase translational success from the laboratory and from our immersive environment into real world operational settings. Digging into some of the specific capabilities, we can look here at the Cairn platform and treadmill. So the platform itself, I mentioned, is on a 6 degree of freedom motion base. And so on the left, you see we can use that to create perturbations, so translations or rotations as somebody is walking or balancing on the platform. On the right side, we can also use the platform to match the environmental terrain. So if you are going up a hill, the platform will tilt back and now you're walking up a hill. If you go down the hill, the platform will tilt forward and so on. The treadmill itself is instrumented such that it can measure ground reaction forces so that we can measure limb loading. We can run our treadmill at fixed speeds or in self-pacing mode. For self-pacing, the user themselves controls the speed of how fast or slow they're walking or running. So if they start to go forward on the treadmill belts will automatically speed up to keep them in the center. And likewise, if they start to drift backwards, the treadmill belts will automatically slow down. And that way the person can walk or run at their own pace. It is a split belt system, so we have left and right belts on our treadmill, and we can run those belts synchronously or asynchronously, depending on the scenario we want to create. And finally, the treadmill itself can go up to 6 meters per second, which is equivalent to a 428-minute mile pace. So we can get people running pretty fast. Another core capability of the Cairn system is our ability to analyze movement. We do this with gold standard electromyography or EMG and motion capture. So we have a 16-channel electromyography system, so we can measure muscle activity from up to 16 muscles simultaneously. And with motion capture, along with 8 video cameras, we can do marker-based motion capture that you see there, where you create kind of a stick figure from the markers placed on the body, or with markerless now, just video-based analysis of somebody's movement. From our stick figure that you see on the left there, we can then create musculoskeletal models, which help us quantify the 3D kinematics and 3D kinetics of the body as somebody is moving. That includes the positions, velocities, and accelerations of the limbs, as well as the forces, the moments or torques, and the powers of the joints. And on the right side of the screen, you see some example signals there of vertical ground reaction force, knee flexion extension, ankle power, and gastrocnemius muscle activity. And all those signals are synchronized together. So as somebody is going through a scenario, as they're walking, as they're running, we get all of this information synchronized together so we can understand how somebody is moving and how somebody is responding to a particular environment. Our immersive environments are created with our projector system. So we have 8 projectors that project their images on the inside of our dome, and those are warped and blended into a seamless 360-degree environment. Most of our scenarios are driven and run in the Unity 3D gaming engine, so anything that you can develop in Unity, we can project. In the upper left corner, you see graphically developed environments that you might see in a video game. We can also map environments with LiDAR. You see the LiDAR point cloud in the upper right corner. With that point cloud, we can then interpolate that cloud into terrain. Additionally, we have 360 video, and we can project in infrared, which allows us to perform night vision applications. So with our immersive environments, we're able to develop construct validation with controlled immersive environments, all of which have comprehensive ground truth. Adding some more capabilities to the mix, here's an example of using biofeedback and multitasking. So on the left, you see a biofeedback example. We put markers on the feet, and the baton is moving according to how fast somebody is walking. And in this particular application, the task is to match a step rate to the targets that come. So they have the biofeedback of the baton, that is their feet moving, and they can target those, they can attempt to step on those targets as they fly through. Any signal that we can measure, we can use and project as a biofeedback signal. On the right, you see a multitasking example where a person has markers on their hands, and there's birds flying towards them. The goal is to hit the birds as they fly by, but at the same time, they have to adapt their gait to the slopes that are presented and walk at a set speed that may or may not be the speed that they're comfortable with. So they have to multitask, put everything together to successfully complete this scenario. So with the biofeedback and multitasking, we're also able to develop environments that have adaptable complexity, so they can either get more and more complex and more difficult, or more and more simple as a scenario goes on. And by incorporating biofeedback and multitasking, we can use these to optimize training paradigms. A big part of what we do in the Strive Center is validate sensors and algorithms. So in this case, this is an example of validating a test system for eye tracking. And so we have our test system, a shimmer system, which contains an IMU, or an inertial measurement unit, and electrooculography. And we can compare that against the gold standards of motion capture and video eye tracking. You can see the video eye tracking where the gaze on the dome, the person's gaze is measured by that green circle, and we can track the gaze as it changes from the crosses on the screen from one to the next. And by doing this, we're able to then test directly compare our test system, in this case in the black signals, with our gold standard in the blue signals. And you can see that the signals in this case are quite similar, but there are some slight differences. After this direct comparison, in a particular scenario, you can determine if the accuracy meets the needs of your goals, of your program goals. If it does, fantastic, then you can likely go forward and use that test system. If it's not, you can either try another test system, or you may need to keep working on the development of that test system until it meets the accuracy standards that you're going for. So we're able to integrate a variety of sensors into the Cairn system for validation against the gold standard equipment that we have. Putting all of these capabilities together, we can use the Cairn system as a synthetic training environment. Here you see an example of a land navigation training environment where we developed a 25 square kilometer scene. And we define the scenario and environment according to our program needs. We're able to integrate and validate sensors within this environment, and then we can limit or enhance information as necessary. Here you see that the scenario is quite bright. It's a blue sky, easy to see the trees in the ground. We can make this much more difficult by changing it to nighttime or to dusk, or potentially to bring in clouds or fog, which will really limit how far somebody can see. So depending on what you're looking for, depending on if a participant is new or advanced in this training environment, you can either limit or enhance information as necessary. As I mentioned before, we can include real-time biofeedback from any signal that we can measure, and then the whole time we're able to quantify performance. A nice capability, particularly in training environments, is that you can compare to expert benchmarks. So if we had an expert in land navigation, we could have them run through this scenario, and then with novice users, compare their performance outcomes with those expert benchmarks. As somebody's going through these training environments, we can also incorporate adaptive difficulty. So if they're doing well, the scenario can automatically get more and more difficult. If somebody's doing poorly, the scenario can automatically get easier until it reaches the balance that you're looking for. And in this way, we're able to enhance learning and training skills interactively, and it also allows us to develop and compare training paradigms. So all of this allows us to integrate capabilities, control our information flow, and ultimately quantify performance. A complex adaptive testbed like the Cairn system also enables multisensory experimental designs. So in the case of static and dynamic balance control, the balance control itself involves multiple sensory systems, such as the vestibular, visual, and proprioceptive systems. If we perturb either the visual environment or our platform environment, either quickly or slowly, we can test a person's reactive or tracking abilities and test if deficits in one or more of these sensory systems exist. So for example, if we could test the visual system alone by just perturbing what we project visually. We can do congruent or conflicting perturbations as well. So we can have the visual system and the platform system move together. For example, the visual system and platform would both rotate downwards, or we could have conflicting perturbations where the visual system would rotate downwards, the platform system would rotate upwards, and we can measure how a person responds to those perturbations. And you can see the systems in blue there are insufficient for corrective action if relied upon on their own during these different conditions. And so we put this type of testing paradigm and experimental design into action with a group of individuals with mild traumatic brain injury. These are individuals who, when they went to their clinician, the clinician did tests on them. The tests came back negative, and so clinically they were okay to go and were turning up as you have no deficits, no problems. But the people themselves with the TBI were saying, well, that's not right. I'm still feeling something is wrong, something is off. So we developed this testing paradigm, and what you'll see in the video on the top is a neurologically intact person walking down an endless hallway, and you can see the platform rotates unexpectedly. And this neurologically intact person, they adapt to that. They have a little bit of adjustment they have to make, but they can adapt pretty well. Same thing happens with the person with mild TBI, and you can see a much larger response there. And our system allows us to quantify these changes. So using the motion capture, using muscle activity from electromyography, using our contact force, we can measure how somebody is functioning before the perturbation, during the perturbation, and after the perturbation. And the outcomes of this particular study led to our ability to identify deficits better than the clinical tests. So on this graph, you can see clinical tests. On the lower left, the clinical tests are in open circles. There's cognitive, motor, and combined clinical tests, and their discrimination ability on the y-axis there, where right around chance, up to just under 60% ability to discriminate whether or not somebody had a TBI. And then when we did our standing trials in green and then our walking trials in blue, performing our tilt perturbations and our translation perturbations, you can see that we were able to discriminate better with the standing trials and really well during our dynamic balance walking trials. And we achieved perfect discrimination on 2 of our tests. So using our complex test bed, we were able to discriminate mild traumatic brain injury deficits better than the current clinical tests allow. So those were some examples of how you might put all this information together. And overall, the STRIVE Center, we have 4 core research areas that align with our group's mission areas. So clinical, operational, technology development, and training for success. In the clinical domain, this might include rehabilitation protocols and physiological modeling. Operationally, we can do things like model environments for humanitarian assistance, humanitarian assistance and disaster relief, mission planning, medic machine teaming. With technology development, things like advanced prostheses and exoskeletons, and testing and evaluation of physiological monitoring, and then training for success, looking at training paradigms. How does somebody go from being a novice to an expert in the physical and the cognitive domains? How are people making operational decisions, and can we improve operational decision making? We support all components of the research, development, testing, and evaluation cycle. So in systems analysis and architectures, for example, we can quantify with high fidelity missing human interactions in current modeling and simulation techniques. We do prototyping, where we can explore and optimize co-adaptive and individualized control systems for human-machine teams. User experience and testing, performing early stage rapid evaluation of technologies with end users in simulated operational environments, and then industry and end user transition. The goal is often to translate benchtop and laboratory research to end users in operational environments. Ultimately, our goal is to enable human operators and to ensure that the human component of any mission is successful. And this involves overcoming tactical challenges that might be given through the physical environment, the operational environment, or through performance degraders, and to enhance the human capability, whether that's through individualized training, augmenting technologies, improving team coordination, or improving that human-machine collaboration. And the Strive Center and MIT Lincoln Laboratory in general, we have a number of collaborative contracting options available in ways to work with different industry groups, government groups, academic groups, and clinical groups. So CRADAs are always a good option. So a collaborative research and development with a commercial entity here that results in technology transfer to industry. We're often involved with SBIR and STTRs, where we can do joint research and development efforts with small businesses that address specific government topics and solicitations. The Strive Center is set up for test agreements, which would allow private sector organizations to test their technology with our facility. That's not R&D, but we're able to facilitate that and basically renting out the system for a period of time. There's commercial solutions openings where streamlined R&D subcontracts can be designed to work with non-traditional defense contractors. And there's always the R&D subcontract option where it's just a standard subcontract to perform research and development. So for more information there's a link that you can follow for more information. And of course, I'm always open to collaborating, and I welcome anybody who is interested to contact me. Also want to give a shout out to Harvey Edwards, who's our operations manager, who's involved in all of our testing. And there's a link to the Strive Center there as well. So that you can see our external facing website, and some of the content that I showed you today, you can revisit it there. Thank you very much for all of your attention, and I'm looking forward to any questions that you might have.
Brian, thank you so very much for that incredibly informative briefing. I certainly learned a lot. This is going to be an extraordinary addition to the National Security Research Enterprise. I'm looking at the chat right now, and I don't see any questions, but being a good moderator, I've got some prepared to ask you to keep the discussion going. So I'd like to do that and wait to see if some of our attendees do have questions for you. The first one is, how do you translate and scale outcomes to a relevant environments? For example, clinics, operational environments, after using the Strive Center and Cairn system?
Yeah, so a big part of that translation is working with the end user, right? And understanding if you have some technology and you have outcomes that you're interested in, ultimately, where do you want to use them? How do you want to use them? And we design our protocols to mimic those environments as closely as possible. So for example, if you have if you have a special operations forces personnel who are interested in wearable technology and using that in the field, we'd want to understand exactly how they want to use that, what information they want from those wearable devices, and then we can simulate those environments that they're trying, that they want that information to come from. Likewise, in a clinical standpoint, we can scope out a broad range of tests and kind of narrow down to try to understand what the key biomarkers, so to speak, might be that would be most helpful and most sensitive to get the clinical outcomes. And then we have technology that we might be able to translate and target a more specific technology that can give you those refined biomarkers from there.
Great. I'm still looking at the chat. I do not see a question, so I've got another one for you.
Okay.
If someone's interested in using Strive Center for a study, how do they go about doing that?
Well, the first step is contact me. And then we can have a chat or a series of chats to really understand, what questions you're trying to answer, what challenges you're trying to overcome. And that way we can better understand the problem and together design a protocol that really targets what you're trying to do and get to the information or get to the technology development that you need in order to solve your challenges.
That was a perfect setup for my final question, which is, how much does it cost to perform a study at the Strive Center, and what funding options are available?
Right. So you saw some of the funding or some of the options on how to work with us in that second to last slide. The cost is really going to depend on the complexity of the protocol itself. So from a non-research perspective, you could look at something like a test agreement where you would come to us and say, we want to rent out the Strive Center and be able to do some motion capture and have people walk up and down slopes, core capabilities that we have, and we could rent out the system and support the data collections for you on kind of a day-by-day basis. The test agreement from that standpoint would cost about $10K per day. But then from a research standpoint, the cost would really like I said, depend on the complexity of the protocol, and we would just build in the time that we would need to support the protocol development and then the testing itself. So it really depends on the breadth and the scope of that research, but it all comes back to, working with me, working with our group office, and making sure that we're able to understand your needs and develop the options there. And then we can go through the mechanisms of funding, whether it's a CRADA, whether it's a test agreement, whether it's a research contract or a government research contract as well. That could be an option for us.
Wow, what a webinar this has turned out to be. I do not have any questions in the chat, so I'd like to ask everybody out there to think one more time to see if there are any questions, and if not, I will give you back the rest of your afternoon. I cannot thank everybody for the gift of their time, and Brian, a truly extraordinary presentation. I sure learned a lot. Thank you so much, sir. Any final thoughts, sir, before we secure the webinar? Okay, so with that, I thank you on behalf of the Federal Lab Consortium, and I wish all of you a great Tuesday afternoon.
Thank you all very much.